We're going to go straight to the talk by Professor Cabrera. And so Humberto Cabrera is a native of Cuba. And he's now working, he's a researcher at the Abdus Salam International Center for Theoretical Physics, ICTP, where I am. And he coordinates the optics laboratory. But he also does many other things. He's remarkable in the ability to help develop careers for young people from developing countries. He's done more than anybody I know on the planet in that regard. So he's got a lot of lessons. He's changed his field. He changes it often. And he's done a lot in quantum technologies for laser systems and metamaterials. But currently his research activities are focused on the development of affordable photothermal and laser-based methods for thermal optical characterization of metamaterials. But he's going to talk about ultrasensitive and affordable methods for efficient cancer phototherapy, which I think is a concern all around the world. So, Humberto, are you with us?
Good morning, good afternoon, Joe. Good afternoon, everybody. Can you hear me?
Yes, I can. Please go ahead and
Can you see my presentation?
We do.
Okay.
Yep. Go ahead.
Okay, Joe. Thank you for the introduction. Thank you to all the organizers for inviting me to be virtually in Ghana. We are doing a lot for Africa here. We are receiving students for training and education. But today I am not speaking exactly about quantum technology, but I will speak a topic that is more related to education and skill development. And also I am happy to present here my research activity related to ultrasensitive and affordable methods for efficient cancer photothermal therapy that I hope and I think is also important for Africa. This will be the outline of my talk. As I mentioned, I will go through the education and skill development at the International Center for Theoretical Physics. And of course, I will describe the research activity at the optics lab in which we are, me and Professor Johnny Emela. And as I am dealing with my activity are focused mainly to training and research of the visiting scientists coming from developing countries, including Africa. I will describe the fundamental of photothermal spectroscopy. Is what we are mainly doing in our lab. I will describe why photothermal spectroscopy is a highly sensitive method and why it's affordable method, low-cost method that can be implemented in any country, including Africa. And as I am related to the work is related to the cancer research, I will explain how we perform the synthesis and characterization and, of course, biofunctionalization of gold nanoparticles and gold nanostar. The photothermal effects and thermal length spectroscopy setup will be described in details and the measurements that we performed. And finally, I will conclude. These are the main activity that we are dealing with here at the International Center for Theoretical Physics. We have thermal length spectroscopy, thermal length microscopy, that is a branch of photothermal spectroscopy. And with this also we deal with detection methods for biosensing based on gold nanoparticles and gold nanostar. We also use online detection method for microfluidics, and we combine with different separation techniques because the technique is mainly highly sensitive but not selective. For example, electrophoresis. Beam deflection spectroscopy is another kind of photothermal spectroscopy that can be used for material and metamaterial characterization to describe the thermo-optical and optical properties. We are also working in a project, FAMU project, Physical and One, that is a high precision laser spectroscopy to measure the hyperfine splitting in the ground state of the muonic hydrogen. It's a collaboration project, FAMU project. And another very interesting technique that we are developing here is digital holography microscopy and photothermal digital holography, mainly for morphological characterization of biological and not biological samples, and for 3D imaging. As Joe mentioned, we are working with developing countries. We receive a lot of visitors, students, also researchers from different parts of the world, from Iran, from Togo, from Pakistan, from India, Pakistan, Senegal, and so on and so forth. Working in these projects that I mentioned before, photothermal spectroscopy, physical of muon, also with digital holography microscopy, and in the past also with optical tweezers. These students mainly came here through these different programs that maybe already Professor Johnny Emela presented to you. These projects are mainly training and research in Italian lab, a STEP program for PhD thesis in cooperation with IEA. Also, there is a program of associate, senior, junior, regular and senior associate, in which applicants can come here and stay 3 to 4 months and develop their own projects. We have also another programs that allow these visitors to come here to the ICTP. And also, we had a lot of good results. Some of these students that I presented before, they developed here their PhD or master thesis, and they, of course, as you saw this, they publish papers, and they propose new projects. They got projects in collaboration with us. And as you can see now, this is a publication in the SPI, the Society for Optical and Photonics, that is supporting our stay here, our research, is supporting the development of this lab, and also bringing researchers and students to the International Center for Theoretical Physics. This is one very good example with Isma Javed. She recently finished her PhD thesis in Pakistan, but before that she was in our lab during 1 year. And I mentioned that this is a very good example because she arrived without any knowledge, without any skills in experimental physics because of the limitation, in developing countries. But she has and she has the talent to do that. And she was mainly designing metamaterials, but she didn't have the way or the lab where to characterize these materials. And then we found here, and since that time I started improving our facilities to characterize these materials. And with her presence here, we really advanced a lot and published very good papers. Now I can say that she is a very good experimentalist. She's able to even to develop her own lab in Pakistan. And this I am happy that we contributed to this. Another important activity that we are dealing with is training through schools, with focus on both lecture and hands-on experience. For example, last year we organized. I was a director of the summer optics school in Nairobi, in Kenya, together with my colleagues from Pakistan. As you can see in this picture from the left side, And from the right side, Dr. Qasim Mahmoud, that is the supervisor of Isma Javed in the middle, and me, dealing with Kenyan students in exhibition during the poster section. We show there our own developments of low-cost device and microscope, conventional microscope and digital holographic microscope. And also we had hands-on activity with these students and computer rooms, also computer lectures. This was a very nice activity. Also, we are using the lab here in Winter College on Optics. Every year we have the Winter College on Optics, and during this Winter College we have also lectures, mainly in the morning, and in the afternoon we have hands-on activity where the students, the participants, they have the opportunity to go and to touch, to put hands on, and to develop their own projects. These are also another kind of activity, outreach activity we are doing here in Trieste with high school and secondary school. We had different activity, also maker fairs, in which the students come and we motivate them to study, to know optics and to involve optics in their life, and to motivate them to study optics. Having this in mind, now I will go to the one of the research that we are doing here, and recently we published in a high impact journal, Small Science, of course, also in collaboration with one student from Sudan that was doing the PhD here. The main motivation for this activity was that in photothermal therapy of cancer, we need it's a challenge, no, to achieve and to deliver the thermoplasmonic nanostructure to the tumors, where we want to, for example, irradiate with laser without affecting healthy tissue. This active targeting with synthetic molecular complex, the idea is to target some overexpressed factors or proteins that are present in cancer, in malignant cells. And in this way, we can recombine with anti-cancer therapy, for example, delivering some monoclonal antibodies. This antibody, for example, there are there is a technique now based on this fibroblast activation protein, FAP protein, that are overexpressed in most of the tumors. Then it is important to develop this kind of, let's say, therapy or immunotherapy without side effects, because most of the therapy nowadays, they produce some side effects. Then we need to be very precisely delivering this antibody only to the target molecule or cancer cells. Another important motivation to develop this work is to use gold nanostar. Usually people use gold nanoparticles, but with gold nanoparticle, the surface plasmon, the absorption of this nanoparticle is indivisible, around 520 nanometers. Then the light used to irradiate this surface plasmon resonance to destroy these tumors is not penetrating in the human body, because the transparency is mainly near to the infrared, after 700, 800, 900 nanometers. This is why we propose this work and develop this gold nanostar with absorption in the near infrared. Also, this work can be, in addition to the photothermal oncotherapy, it can be used for photoacoustic imaging to image this tumor and to know the limit of these tumors. One of the problems that I mentioned is the selectivity targeting these cancer cells while sparing healthy ones, and to have a safe standard when treating a patient. And these humanized molecular antibody or antibody fragments, such as single chain fragment, this is what we are proposing to use in this work. We call SCFB. In the future, I will call this. Are present, are example of such targeting moieties, particularly used in cancer research. The idea of this fibroblast activation protein, FAP proteins, to target microenvironment is this, is here in this scheme. There are some cancer-associated fibroblasts, CAF, that are key components of the tumor microenvironment. They favor the growth of these tumors and play crucial roles in tumorigenesis and progression of these tumors. But these CAF elements produce these fibroblast activation proteins. Therefore, everywhere in cells where you can target this fibroblast protein or FAP protein, then you identify a tumors, and then you can irradiate this tumor with different photothermal therapy and to destroy the tumor. This is a new therapy that is very promising, using gold nanoparticles and gold nanostar to target solid tumors. I am giving here one example, very briefly, of different therapy that people are using, and this therapy mainly generate side effects, osteotoxicity, and even death. In some cases, they produce muscle damage, and this is why it's useful to identify treatments that selectively kill this FAP protein associated with some kind of cancer without causing systemic toxicity, which would permit treatment that aim to deplete tumor associated to these proteins. This is how we, let's say, present our work, and we motivate to do that. As you can see from the left side here, we have this is the antibody that we are using. One of the antibody, we are using two antibodies connected to a peptide. The peptide acts as a connection between the antibody and the gold nanoparticle in the process. And why we are using this gold nanostar here, gold nanostar, and we compare with gold nanoparticle. As you can see here, the absorption of gold nanoparticles is around 520 nanometers. However, gold nanostar is around 800 nanometers. This is another kind of nanoparticle used also in cancer phototherapy. And here in this picture, you can see how the penetration depth is better using gold nanostar or light at 800 nanometers. And here is the temperature field around this gold nanoparticle or nanostar after irradiation with a specific light. You can see that in the case of gold nanostar, the temperature field is higher. We will demonstrate this after. Because of this structure, the light to photothermal energy conversion is more effective. And to this right side, we present the motivation of the work. We developed this gold nanostar and gold nanoparticle, and we functionalize with this peptide and connect the specific antibody that will be connected or will identify these FAP proteins. As you can see here, these FAP proteins are overexpressed in any cells surface as a layer, and then as they are connected, they are ready to be radiated with laser and to be destroy the cancer effectively. This is the main mechanism of this phototherapy. I will describe very briefly the photothermal therapy process, very briefly, because it's not the most important here. First, there is absorption of light. This light is converted to heat, then increase the temperature in the medium. There are density change and refractive index change that we produce with one laser, but a second laser detect this refractive index change, and these changes are related to the strength of this signal. You can see there is signal because the second beam change the intensity according to the absorption coefficient or the absorbance of the sample, the excitation power, and some additional parameters. Then we can characterize any sample, we can measure the concentration of this sample or the thermo-optical parameters, measuring the signal. Why this technique? Which are the advantages of this technique? It's very high sensitivity. It means you can measure very low absorbance. You can couple this technique with, for example, with fluorescence. You can couple with microfluidics. It's a free scattering method. This is why we can use gold nanoparticles without affecting the measurement. It is an online detection method. It's a non-destructive method because we use, as it is very sensitive, we use very low excitation power. It's a single molecular detection method, and the most important is cost efficient. It's very low cost. Then we can implement in any laboratory. Then why is very sensitive? First of all, it's very sensitive because it's a cumulative method. I have one example here. If we excite an atom or molecule during a few milliseconds, because we produce excitation beam that is modulated in intensity at 1.3 Hertz, then it means we excite this atom or molecule during few milliseconds. However, the absorption of an emission of atom of molecule is of the order of 10 to minus 11, and the relaxation thermal process is around 10 to minus 3. It's very slow process. Then if you divide this, the ratio of this is 10 to 8. It means that during only one excitation cycle you can excite a single atom many times. Then the energy is accumulated in this atom, and this is why this technique is very sensitive. But in second place, it's a phase method. This method has a phase character. It means that we measure the intensity, but the intensity is related to the phase. And the phase contains the length of the sample and the wavelength of the probe beam. Of course, it's proportional to the temperature variation, but these are very small change. The length of the sample can be 2 millimeters to 1 centimeter. The wavelength of the light is 10 to minus 9 nanometer. This means this ratio is very high. This is why we have a huge phase change in this medium during excitation. It means we can measure and we can have a signal that is very, very high. Going to the synthesis and characterization and biofunctionalization of the gold nanoparticles and gold nanostar, we first add this peptide called A5B9 to connect to the gold nanoparticle, but we need to know first if it is stable after this solution. This is why we add a different concentration, and we detected that at 5 microgram per milliliter, the solution was very stable. Then we keep this as the initial concentration. Then we need to add the antibody. The antibody, here we have two kinds of antibody, SCFB and EGG4. And for this antibody, when you see in red the solution, it means it's stable. When it goes to blue, it means it is unstable. This is why we realized that 5 microgram per milliliter was the best concentration or the limit for this kind of antibody. For this antibody, the concentration was 10 microgram per milliliter. Then we keep this as the optimum concentration. After that, we performed transmission electron microscopy measurement to see the size of the nanoparticles, and we corroborate that was around 20 micron for gold nanoparticle and 32 nanometers, excuse me, for the gold nanostar. Then absorption measurement corroborate that the absorption peak of the gold nanoparticle is around 520 nanometers, and for gold nanostar around 800 nanometers. What is telling us that we have to use a laser to excite this gold nanoparticle here, and a laser around 800 nanometers to excite the gold nanostar here, where the surface plasmon is. Then we saw that after adding this antibody, the peak shift a few nanometers to the red is red shifted because the size of the particles, as you can see here, increase. When the size increase, usually there is a red shift, and we measure the particles, the targeting molecule with antibody for the gold nanoparticle and for gold nanostar here. Then after that, we propose to use a photothermal setup to characterize these gold nanoparticles using photothermal spectroscopy and infrared radiometry. For this setup, we propose to have excitation laser to excite the sample here, the gold nanoparticles here with the antibody, and a probe laser that will detect the intensity variation with a pinhole and the oscilloscope to see the signal. We use the laser that excites the gold nanostar at the plasmon resonance around 800, and for the gold nanoparticles, and the probe laser another wavelength. After that, we use infrared radiometric camera to see the photothermal conversion, the light to heat conversion, that is very important in this gold nanoparticle and gold nanostar. Here we can see for the gold nanoparticles, okay, this is the setup here, a camera with a detector. You can see here the temperature field around the gold nanoparticles using the different lasers, and we excite the gold nanoparticles here, as you can see here, using 744. Of course, this doesn't correspond to the surface plasmon resonance. Then when we match with the absorption band of this, you can see that the temperature increase more because there is more optical to thermal energy conversion. Then we use photothermal spectroscopy to characterize gold nanoparticle and gold nanostar. This is the laser on, laser off, modulated. We show that in the buffer without nanoparticle there is not any thermal conversion, and after that we excite the gold nanoparticles using 780 nanometers. Of course, this is not the plasmon resonance. This is why this signal is very low and very noisy. As you can see here, the noise is very high. Also, we show that the signal optical to thermal conversion decrease with increasing the nanoparticle size. This is why we keep 20 or 30 nanometer as the best nano size. Then we can see here, if we excite the gold nanoparticle at the plasmon 520 nanometers, the conversion is higher, the signal is higher. These are the signals for different concentration of these gold nanoparticles and for 20 nanometers, okay? But for the gold nanostar, we realize that using the same power, of course, excited at 780 nanometers, and the gold nanoparticle at 500, at the plasmon, the gold nanostar produce more heat using the same power. The red line represents the higher signal in the case of of gold nanostar, even at low concentration that the red here for gold nanoparticle. It means that they present higher photothermal conversion. This is why we propose to use gold nanostar for photothermal therapy of cancer. And after that, of course, we performed different measurements. For example, we measured with jet electrophoresis. For example, here you can see here that this is the gold nanoparticles or gold nanostar here with the antibody didn't move in the gel because of the higher bigger size than this without the antibody.
Hi, Humberto. You've got about 30 seconds left. Could you just skip to the conclusion, please? Sorry.
Yes, I'm going. This is the last slide. And then we also did some additional measurement as like fluorescence to show the binding of these gold nanoparticles even with cancer cells that we're trying to target. Then this was my last slide, and as a conclusion, we can say that we developed very efficient photothermal therapy using gold nanoparticles that absorb in the near infrared, where there is superior photothermal conversion, and also the light can penetrate more in the human body. The technique that we use show very high sensitivity, and we detected the difference in very short period of time. We prepared the solution; they were very stable. We also functionalized with the antibody; they were stable, and we did some experiments using cancer cells. But still, these experiments are going on, and we'll present the results next time. Thank you very much for your attention, and if you have questions, I am ready to answer.